next session, which is on vector control of induction motor drive. Myself, Dr. Balamurugan. I'm working as an associate professor in the Department of EEE, KS Rangaswamy College of Technology. So in this session, we are going to see about the vector control of induction motor. So before going to see the vector control of induction motor, we have to see some differences between induction motor drives and DC motor drives, because in industries we are using induction motor drives and also DC motor drives. So why we are going for induction motor drives instead of DC drives? So here we can see some of the differences. So induction motor is simpler, smaller in size, and also less maintenance, less cost, capability of faster response compared to that of the DC drives. And also we can have a speed response is also good compared to DC drives. So instead of induction motor drives, we will be go for DC motor drives also. And DC motor drives, we can see the first major advantage is you can have an easy of control, and performance will be high compared to that of induction motor drives. And the first main thing is here, there is a decoupling between the torque and flux components, so that the control will be individual. So when we are controlling torque, the flux will not be altered. When we are controlling the flux, the torque will not be. So the basic methods of control, we can see conventional control is a scalar control of induction motor. And why we are going for vector control means scalar control has some limitations like sluggish response, stability of the system is not good when we will go for continuous control. And name itself, we can say it's a sluggish control for induction motor drives. So here we can see some of comparison between scalar control and vector control. So the control of current and voltage frequency magnitude will be good in scalar control. And here in vector control, we can control have a magnitude, phase currents, and voltages based on the dynamic models. Here we can control in scalar control based on the steady state model itself. So in transient conditions, we cannot go with the scalar control, but in transient conditions, we can go with an vector control, or we can also say it as a field orientation control. And performance will be best for low best for induction motor drive is vector control drive, and scalar control drive we will be getting a low performance only, and the implementation of control will be simple in scalar and it will be complex in vector control. So you have to have some observe the vectors and calculations will be more. And here the coupling of torque and flux will be there. So both are functions of voltage and frequency. But in vector control drive, both will be a decoupling in nature, similar to that of the DC drive. So here in scalar control, the control itself sluggish and it will not be unstable. Here in vector control, we are using decoupling components of torque and flux. So control will be quite appropriate and also best suited for all applications of where AC drives used. The same thing. More complex mathematical calculations are needed for vector control, but here the simpler control in scalar. So dynamic response will not be good, but when we compare to that of vector control, excellent dynamic performance will be there. And power dissipation is also high in scalar. Here in vector, there will be low power dissipations. Let's we see vector control in depth. So before going to see, we will compare the DC drive and an induction vector control induction motor drive. Both will be same. So compared to that of the component, torque component and field component decoupling nature. So here in this slide, I am showing the separately excited DC motor. equivalent components, and also vector controlled induction motor equivalent components. You can see the nature of the components. That is the armature current, which is perpendicular to that of the field component. So here we can say the torque component and field component will be a independent and decoupled. So when we are saying, when we are controlling individually, we can have a control over the motor. The same will be observed in the induction motor vector control. Here also we have modeled the same like that of the DC drive analogy. That is separately excited DC motor. Here you can see the torque equations, which is given as a KT, IA, and IF for separately excited. Here torque component is IA and field component is IF, and the armature current defines the control of torque. Field current defines the control of field component. So same way here also we have modeled the same structure which is followed in that of the separately excited DC motor drive. Here we can see the torque component is IQS, which is equal to that of the IA, and IDS, which is nothing but which is equal to that of the IF. Here the torque component is IQ and field component is ID. So same procedure we have followed in separately excited DC motor. So we are modeling the separately excited DC motor analogy with that of the vector control induction motor drive. Here in vector control induction motor drive, we are converting the components into director axis and quadrature axis component. Then we are controlling the inverter. Thereby we will be getting the good dynamic response of motor control. So here I am giving some components description compared to that of the separately excited DC drive and also the induction motor. Here you can see the field component flux, which is perpendicular to that of the armature component. So we can say torque, which will be given as K into phi F into IA. So phi F can be written as, that is flux component can be written as IF into IA sine 90 degree, because both component will be in 90 degree perpendicular. So keeping the phi F as constant, we can have a phi F as constant, we can have a control over the torque component. So T. So the same which will be given for induction motor drive. So here the flux component, that is rotating component, psi R and psi S is given. So here psi S is produced by the stator currents and psi R is produced by the vector is produced by the rotor currents. Both are vector component and both will be controlled by appropriate stator currents and rotor currents. That is which is induced in the stator, that is induced in the rotor, and all which is given by the stator. And both will be rotating in synchronous speed, which is given as omega s. The induction motor equation, torque equation is given, which is compared to that of the DC motor torque. And you can have a comparison over the here, how both will be behave like same. That is induction motor behave like a same. So from this equations, we can have a summary that both torque control of DC motor and vector control of AC motor are similar. And here in DC motor, field current is orthogonal to armature flux. So we can say it as both will be decoupled. So field current controls only the field flux and armature current controls only the armature current. So the induction motor can be modeled as a DC motor like performance when it is converted into DQ reference frame. That is when the induction motor vector control is modeled as synchronously rotating reference frame, means we can have a DC motor like performance or DC motor like control. So here what we are doing is synchronously rotating reference frame is considered for induction motor, and all the components are modeled as a sinusoidal variables in steady state condition. So what we have done is we are taking it as director axis and quadrature axis, which is rotating in synchronously rotating frame. So we are indicating as IDS, which is nothing but director axis component for induction motor, which is equivalent to that of the field current in DC motor, and IQS, which is nothing but a quadrature axis component which is rotating in synchronously rotating reference frame of induction motor, which is equivalent to that of the torque component, that is nothing but IA of DC motor. So next we are entering into the principle of vector control. So here this diagram indicates how vector control is implemented in induction motor. There are two types of transformation is done, which is for control structure and also for machine structure. So initially we will call it as inverse transformation. Next we will go for the transformation. So here we are converting the director axis, quadrature axis components to ABC model. Then again that ABC model is converted to director axis, quadrature axis. This is the process done for vector control. This is the basic principle, and all these are done with respect to that of the unit vectors cos theta e and sin theta d. Based on these unit vectors, the conversion is done in the control structure and also in the machine structure. So at the last, we are getting the perpendicular director axis and quadrature axis for having a decoupling nature. So initially you can see quadrature axis components are converted into director axis and direct axis and quadrature axis, which is rotating in stays synchronously rotating reference frame. It is nothing but stationary reference frame, which is converted into synchronously rotating frame. That synchronously rotating reference frame is again converted into ABC quantities. That is the block which is shown in the second of the control section. Again, in the transformation of that machine model, ABC reference quantities, which is taken as a feedback, which is converted into director axis, quadrature axis in synchronously rotating reference frame. Then again, we are converted into machine models. That's all about the principle of vector control. By this inverse transformation and transformation, we are getting the director axis component, quadrature axis component for controlling the induction motor. That's all about the principle of vector control. And from this discussion, we have concluded that by decoupling nature, we can have a precise control of induction motor. So for that, we are following the DC drive decoupling natures, and we are generating the vectors. Thank you for listening. Thank you.